Welcome, this is lecture number 39. In this lecture, we are going to talk about design of current mode control boost converter. Here, we are going to consider traditional approach of output feedback approach for design of current mode control. Then we want to consider another approach, alternative approach, the state feedback design approach, but it is under current mode control. So, first we will design a boost converter under current mode control. Then we will check the model validity using MATLAB AC transient simulation. Then we want to find out what are the limitations using output feedback design approach. And finally, we are going to consider the design using state feedback based approach. So, we will start with, in fact, in the previous lecture for a buck converter, we found that a first order model is sufficient if you do not consider any ramp compensation, or if there is no subharmonic, right. But in case of ramp compensation and subharmonic, then it is better to use discrete time model. Otherwise, the design that I am going to consider, it is much like a less than 0.5 duty ratio. So, where the first order model will work perfectly fine up to the certain bandwidth, that means crossover frequency. So, here first I will take the first order transfer function of the boost converter, where this approximation is 1 ESR0 and then 1 RHP0 and 1 pole, because here again the inductor is replaced by a control current source, and then using the first method of approximate small signal approach, we can obtain the first order transfer function. So, 1 0 due to ESR, 1 0 due to RHP0, but 1 pole. But please remember, generally we are familiar that this is a improper transfer function because it has 2 0 1 pole, but actual system has 2 pole because there is a physical inductor. Since we are getting the approximate model, that is why we are writing, otherwise this model, this is not a practically realizable system, but here we are taking the approximate version of an original boost converter where there is originally 2 poles, right, there are 2 poles. So, here all these parameter like a DC gain of the plant, it is given, ESR 0 we know, then RHP 0, it is same as voltage mode. What I mean, even if we take open loop converter, voltage mode, this RHP 0 remains same here, and the pole actually we can obtain from this model. So, this we have discussed already earlier. Now, in boost converter we want to design a closed loop control, right. So, that means we have to shape the loop transfer function. So, that means our open loop control to output transfer function, open loop means here the inner current loop is closed, but if we consider this one as if we disconnect the outer loop, then we have a control current reference, and that is why we got GVC. So, this transfer function we have discussed, it has one RHP0, and we have discussed the RHP0 comes close to imaginary axis under high load and high voltage gain, and that will lead to severe bandwidth problem, because we will see when you want to design a compensator like a crossover frequency, if you want to achieve certain desired crossover frequency, then that crossover frequency will be limited by the RHP0. So, if the RHP0 comes close to the imaginary axis, the bandwidth of the boost converter will be really very low bandwidth. It also has one ESR 0 which is located at very high frequency for low ESR, and we will ignore this effect momentarily because this is located at very high frequency. Then we have a single pole, and that pole, if the load resistance is high, then it will be a slower transient performance, and the DC gain we will figure out, it is basically a load dependent term as well as a duty ratio dependent term. So, it leading to poor load regulation as well as line regulation here. Even though the current mode control has an excellent line regulation, but for boost converter it is not as excellent as like in a buck converter. It is better than voltage mode, but in terms of, because there is a dependency in the closed loop, that means the DC gain, there is a duty ratio dependency. So, if there is a change in input voltage, duty ratio will also change. As a result, there will be a slight shift in the DC gain of the control to output transfer function. Now, the primary loop shaping objective, we need to compensate for RHP0. Okay. So, that means in order to achieve flat gain, so we will consider one pole of the controller which will be placed in coincidence with the RHP0. So, our controller should have a stable pole, because we we should not use the unstable pole to cancel unstable 0, because unstable pole 0 cancellation will make the system internally unstable, right. So, the controller pole must be stable, but we will place the pole in coincidence with the RSP 0. Then ESR 0 compensation, it is not needed if the ESR is very small. So, in fact, I will show you the case study where we took some ESR, but still the model matches accurately because the ESR is low. And then we need to cancel the single pole here by means of a controller 0. Okay, so we want to place so that means now another we need to consider one integrator, because the integrator is needed to achieve close to 0 steady state error, right, or basically to achieve very high DC gain, loop gain. And then the compensator, the DC gain of the compensator that we are going to consider, that is required to meet certain crossover frequency. So, that we will discuss in the design process. So, in this case we will find, since we need 1 0 to cancel this pole of the system and 2 poles including 1 at origin. So, this represents a type 2 compensator. So, here PI controller is not enough. So, in voltage mode, in current mode control boost converter, we should not use a PI controller, particularly for this approach, because the PI controller, I mean, we have only 1 0 and 1 pole, right, and that is not sufficient to shape the loop. So, here we need 2 poles and 1 0, because 1 pole, additional pole is needed to anticipate the effect due to the ESR. We want to place in coincidence to ESR. But once we go to state feedback design, then we will find approach design, the PI controller should be sufficient. So, in this output feedback approach, because we do pole 0 cancellation, we need a type 2 compensator. Now, for a perfect boost converter, that means if we ignore the effect due to ESR, because ESR is located far away and we are talking about the control bandwidth which is limited by the right of plane 0. So, if the right of plane 0, that means your load is high, ESR 0 is negligible because it is far in the right hand side. So, its effect is negligible, because your control bandwidth will be much lower than the RHP 0, right. So, the ESR effect can be neglected. So, this is my approximate transfer function with 1 0 1 pole and 0 is the ESR 0 of the plant. Now, the controller we talked about, it is a type 2 compensator. So, in type 2 compensator, we need to place controller 0 to cancel the plant pole, right, and we need to place the controller pole to in coincidence with the RHP 0, that means in coincidence with the RHP 0, right, but it is a stable pole, remember, right. Now, with this, the loop transfer function, that means if we place this and this get cancelled, sorry, this and this get cancelled, that means the stable pole of the system is cancelled by the stable 0 of the controller. But we will have these two as well as one integrator, DC gain of the controller and the plant DC gain, and we are placing the controller pole in coincidence with the RHP 0. So, loop transfer function will become like this. Now, since you will find you have S by omega RHP, right. So, I want to write this as well. So, if I write S, then I can write S by omega RHP into omega RHP, right, and this is exactly I have done. So, that is why this term is coming here, and so now it is S by omega RHP, and this term is my KL. Now, why I am writing S by omega RHP? Okay. Now, we want to replace this, that means if you go for frequency response, that means if you go for frequency response, we generally write S equal to j omega, because if it is a stable system, generally we write S equal to sigma plus j omega, but for a stable system, that means this sigma term which is associated with the exponential decay, it will decay and it will eventually come to steady state, and then the frequency response we simply take j omega, because we will wait for a long time, so that the system actually, all the transient effect is decay, they are vanished, and it comes to the actual steady state behavior, where we are exciting the system with some frequency omega. So, we are sweeping this frequency, right. So, in this frequency response, if we write S equal to j omega, then S by omega RHP will be j omega by omega RHP, and this we are writing omega n, where omega n is nothing but this. So, that means we are writing k loop j omega n is this. Okay. So, now under perfect compensation, our k loop, we have already written this expression j omega n kl 1 by this term. So, if you obtain the in terms of polar form, that means this particular if you take the whole thing, that means if you take this whole thing, you will see the magnitude of this and magnitude of this, they are same. So, they will cancel each other in terms of magnitude. So, the overall magnitude will be R kl by omega n. This is clear, this can be derived. But if you take phase, the phase due to this will be minus 90 degree, and the phase due to the ratio of these two will be simply minus tan inverse of twice omega n by 1 minus omega n square. So, that means we got the polar form, the loop transfer function. Now, we need to get at gain crossover frequency, the amplitude, the magnitude should be unity. That means, this is the unity at gain crossover frequency, and that means here at gain crossover frequency it is equal to 1, and what is my omega n? My omega n is simply omega by omega RHP, and at gain crossover frequency this will be this will be simply omega c by omega RHP, and this is equal to, this is nothing but my kl. So, we are getting this expression from here. So, you can write, and if we substitute the kl expression, because kl, where is my kl? So, we have discussed in the previous slide, yeah, this is my kl expression, right, kl expression, kg, that is the DC gain of the plant, kc is the DC gain of the controller, and the omega RHP 0. If we write all the expression, then we can get is here. Okay. Next, at gain crossover frequency, we have already computed the gain. Now, how to find gain crossover frequency? Because if we can set the gain crossover frequency, then we can get the controller DC gain, right. If we recall what is there in our controller has a DC gain multiplied by controller has 1 0 and controller had one pole at origin and one pole, and we have set that omega cz to cancel the pole of the open loop system, that means your control to output transfer function. So, this is already well known because we have cancelled. What is omega Cp? This is kept same as RHP 0, RHP 0, sorry. This is same as RHP 0. So, that means we know, and we know the expression of RHP 0. So, that means this is also known. So, these two are known, only unknown is the Kc, and that can be obtained from this expression. Now, the question is, for a given load current, given duty ratio, what will be my crossover frequency? Who will give me the crossover frequency, right? So, there are two approaches. One approach, let us say the crossover frequency is like at k times omega RHP 0. That means either I can take k greater than 1, less than 1, but I will see what will be my k choice, or the gain crossover, that means omega c can be obtained from the phase margin criteria, and we will discuss these two. So, in the first case, at gain crossover frequency, which is omega n dash, that means omega c by omega RHP, let us consider a case study 1 where we are setting k equal to 1. That means we originally choose Kc equal to k times omega RHP 0, and here we are taking k equal to 1. So, omega control crossover frequency is same as the RH0. If we set it, then the Kc can be obtained from the previous. That means we have replaced omega c by omega RHP. And what is my phase angle? Because we know that omega n was originally omega by omega RHP, and that crossover frequency we replace by this, that means dash replace. So, this dash symbol indicate that omega n dash is nothing but omega c by omega RHP. Now, if we set this to be omega c equal to omega RHP, so this is 1, and if you consider this term will become infinity, okay, because there is a in the denominator 1 by in the denominator 1 you will have 1 minus 1. So, it is some constant by 0. So, it will be infinity, and if infinity means tan inverse, that is 90 degree. So, it is 180 degree. So, the phase margin is 0 degree. So, it is not a stable design. So, that means the omega c must be smaller than RH0, and if we get anything better, so phase margin will be negative. So, that is unstable system. So, our gain crossover frequency must be smaller than RH0, but how small, that we will see. So, another approach, the design based on phase margin criteria. So, at gain crossover frequency we know the expression, and the desired phase margin is nothing but 180 degree plus your phase angle at omega n dash, and we are trying to find omega c. This is unknown, and this expression if we substitute we will get this, and if we rewrite, this expression is nothing but tan of 90 degree minus phase margin desired. So, if you set some phase margin, let us say 60 degree, then tan 30 degree, then you can find out what is my omega n dash, and what is my omega n dash? It is nothing but omega c by omega RHP, and this we have taken k, because we have taken omega c equal to k time RHP, right. So, you can find out k from here, and once I find out k, I can find out omega c, and if I can find out omega c, or sorry, you can k, then you can replace here. So, we will first design using 45 degree phase margin. If we set 45 degree phase margin, then for the same process that we have discussed, the omega n dash I will say, the dash that we have just discussed, which is omega n dash, sorry, omega n at omega c, that is omega n dash, okay. Now, here it is omega n, because omega n dash is nothing but it is the omega n dash is nothing but it is the omega n at omega equal to omega c, that is it. So, it is that is what 0.414. So, our omega, that means our omega c will be 0.414 times omega RHP, and we have to check. So, we want to check in this way. If I set in my MATLAB code 0.414 is my crossover times RHP0, then am I getting 45 degree? So, I will check in the reverse way, okay. So, let us check, we want to check using MATLAB, matching case study. So, let us go to the MATLAB. Here we are talking about the boost converter design. So, all these model parameters, load resistance is 1 ohm, and if you go to the parameter file, I have taken the input voltage to 3.3 and output is 5 volt, okay. So, I can set it here. Now, here the switching frequency is 500 kilohertz, RH0 expression, everything is given. Now, this will the design, it will ask for all this what fraction of RH0 we are going to set, and it will match the reference transient response. I have applied a reference transient of 0.2 volt. So, it will change from 5 to 5.2 at 3 millisecond. Let us run it. So, I am select the fraction of RH0, that is my bandwidth. So, let us say 414, okay. If I do it, then my RH0, so what is my phase margin? So, let us go to my phase margin. So, let us see what is my phase margin that I have obtained. So, it is 45.5 and we said 45 degree because we took an approximation 0.414, but actually it is an irrational number, right. Now, if we go to the actual response and you will see that at 45 degree phase margin, this is my response of the converter. This is a reference transient. So, it is changing from 5 volt to 5.2 volt, and you see the green one is coming from the model which is the from AC simulation, and then we have added the offset, that is my operating point, and then we match with the actual switch simulation. They are matching more or less closely, not very accurately, but that is reasonable. Now, if we reduce, that means if we now you make it 1/3, it was, so that means we are making 1/3 and we are finding what is my phase margin. Now, we are increasing phase margin, earlier it was 45 degree, now it is like a 53 degree. Then you will find the response is somewhat better because overshoot has reduced, okay. But you see there is an undershoot behavior. That means the initially instead of voltage going up, it is first going down and then going up. So, this undershoot behavior is due to the right half plane 0, because the non-minimum phase behavior, it will result into some initial undershoot and then it will rise, and this non-minimum behavior will be more prominent once your load current increases, right. Okay. So, and your bandwidth will be really very small, okay. So, this is the design and we match the model and they are matching quite nicely. So, that means we show the model matching. Now, here is the design constraint. That means, if I want to increase the crossover frequency, let us consider again the MATLAB. Here I want to first consider that if I use my phase margin to be, that means let us say I want to achieve 1/3 RHP0, okay. I want to achieve 1/3 first, and it is, we can achieve this. Now, I want to keep this and change the color. So, here I am changing the color. So, green I am using, let us say red, okay, and let us run it. So, here I want to increase to let us say 1/2, instead of 1/3 I want to go for half of the switching frequency, and let us see what happened. So, if you see in the first case, the green one, the matching is perfectly fine with the actual switch simulation, because if you particularly look at this response, the green is following perfectly. But once you try to push the bandwidth high, first of all there is a model mismatch is coming. Secondly, since the phase margin is poor, because in earlier design we saw 53 degree phase margin, here we see the phase margin is 37.5, which has reduced significantly, and lower phase margin will lead to higher overshoot, right, because the phase margin is inversely proportional to, or it is phase margin is some sense it is proportional to the damping ratio. So, if the poor phase margin means you have a smaller damping ratio. So, this is a comparative result. So, the red one is we want to increase the bandwidth, but the cost is, the penalty is your response become, overshoot become higher, and it is something not acceptable, very high, okay, and maybe your settling time will be more or less same, but the overshoot is something which is unacceptable. The another thing, you may have some more additional right half plane 0 because you are trying to push the bandwidth, okay. So, that means what we are trying to come, there is a trade off, higher gain crossover frequency if you want to achieve, poor phase margin. Poor phase margin will lead to higher voltage overshoot because of poor damping, and if your higher phase margin, if you want to set high phase margin because you want to make the response like overshoot, you want to reduce, then it will lead to poor bandwidth and a slot transient response. And the design thumb rule is that generally the crossover frequency is set to the minimum of 1/3 of the RHP0 frequency, comma 1/10 of the switching frequency. It is 2 pi, that means it is in radian I am talking about. So, it is 2 pi FSW by 10, that means 1/10. Because if you take light load, then RHP0 will be farther right side, then your model validity will come in terms of 1/10 of the switch infinity, beyond which it will not work, because that we have discussed earlier. But this trade-off will not allow us to extend the bandwidth or response, because if we want to go further up, then our overshoot is increasing, right, if you want to speed up. So now is there any way to overcome this? Let us go to the AC equivalent circuit of a boost converter, ideal boost converter, that we have already discussed. So this is a AC equivalent circuit. We want to achieve, because we want to design the current mode control using state feedback approach, So for that we want to write the state space model. So from this equivalent circuit, I can take that x1 perturbation is my inductor current perturbation and x2 perturbation is my capacitor voltage or the output voltage in this case, because here if we take ideal, the capacitor voltage is same as the output voltage, but otherwise capacitor voltage and output voltage are different if there is an ESR. Then perturb linear model, if you write the inductor current perturb dynamics from this equation, from this circuit, then you can write x1 perturb dot will be function of this. Similarly, if you write in the perturb output voltage dynamics, then you can obtain the perturb dynamics of the x2 perturb, which corresponds to the capacitor voltage. Here it is the output voltage perturbation. Then we can write down the two state equation perturb, because we are talking about the linear state space model, and for switching converter, after applying averaging and linearization, we are getting the perturb model which looks like a linear system. Then we are now considering a PI controller. So the earlier two state were the state of the original system of the boost converter, but now in the output feedback of the current loop we are using a PI controller, right. So the PI controller Kp into error voltage and Ki into integrator of the error voltage, integration of the error voltage, and the output of the integrator we are taking the x3, that is the another state. So we can write now the third state is this, and we can write down first state we have already discussed, second state we have already discussed, and the third one is the augmented state, which is the derivative of the third state is nothing but the error voltage, and that is nothing but Vref minus x2 perturb. And if we write the perturb state space model, then you will obtain this perturb model, and if you go back in the last equation you also have a Vref perturbation term. So if you want to write down that, then you can also write down there is one more term 0, 0, 1 into Vref perturbation, okay. Then here you can write some ER into Vref perturbation, and this is my ER, this is my E1, this is my B, and this is my A, okay. So now if we take the duty ratio, so it is the combination of the modulator gain. Now we are taking the current loop gain Kc, because if we consider the current loop gain in current mode control, also we can consider a current loop gain, that is this, and this is the proportional gain of the voltage controller, and this is the integral gain of the voltage controller, and we can write in terms of state feedback form. And what is my Fm? Fm I can simply take 1 by Vm, that means I can use a PWM modulator. If you use a state feedback control, the whole error will actually go, because if you go to lecture number 18, we have discussed in detail the implementation of state space and state feedback control. So modulator gain is 1 by Vm, because we will consider a ramp, okay. So here we also have an additional term that we have discussed. So with this we will have ER into Vref perturbation. Here also we will consider the additional term ER into Vref perturbation, and it is ER into Vref perturbation, okay. So this is my closed loop equation, right, and after closed loop again you can add this term with this as well as this, both. This is output equation, then the closed loop characteristic equation will be SI A closed loop. Now coming back, how to place closed loop pole. So it is a third order system including the augmented state. So, the desired closed loop pole can be considered one. First of all, we have to choose the crossover frequency smaller than RHP0, because we discussed even in output feedback we cannot go up to RHP0, we have to be reduced, but we want to increase this k factor compared to the output feedback response. So, the pole due to output capacitor which is set to omega c, that is one pole, the other pole due to the inductor 10 times. Imagine in our output feedback approach we have cancelled the planned pole with a controller 0. That means in the loop transfer function we lost the control over the voltage pole because we have cancelled the pole, right, and that is one of the drawback of the output feedback approach, because of pole 0 cancellation the system may not be controllable. But here we are not cancelling anything, but we are considering the capacitor pole which is set to omega c, and inductor pole we are taking 10 times faster, because typically the thumb rule inner current loop has to be faster. Then the 0 of the PI controller we are to be decided. That means if I take a PI controller for regular current mode control, so we will generally take Kp plus Ki by S, right. So, this will be simply Kp into S plus Ki by S. So, I am talking about this 0. So, that means this you can write, if you take Ki common, I can write this like this, 1 plus S by controller 0 by S. So, this approach was discussed because in this paper, and which is this reference paper we are using almost for the maximum part of this course. Next, in this design, so first we are taking a case study. Let us say we want to take K to be 0.5 if we choose, okay, or we can choose K to be 0.3, 1/3 or whatever. Now, we can set the capacitor pole, inductor pole 10 times faster, and the voltage controller of the PI, let us say A1, which is K integral gain of the voltage controller by proportional gain. So, here we are taking, let us say, some value, that means the case study we are considering, we are taking to be, let us say, some around 10,000. Okay. So, let us go to and take a case study. So, here now we will first design using output feedback control, and we want to first achieve, we want to first achieve here, we want to achieve 1/3 of the RHP0. So, this is my response, right. Now, I am going to the state feedback based design, and if you go to the state feedback based design in the control here everything is same, only I am adding a gain with the current loop, and since I told that there has to be a compensating ramp, because it will work like a modulator, but I am taking a very low ramp, it is just 1 voltage, because your input voltage is very low, it is not very high, 1 volt only, 0 to 1 volt. Now, I am designing this first to obtain my first ratio, I told A1 which is 10,000, that means Ki by Kp. The other pole I am taking minimum of RHP0 by 0.5, I can take, let us say 0.33, because I want to compare first, or 1/10 of the switching frequency, right, and then I want to match this response, and for this case I want to use a different color. So, let us say I want to use green color, not green, I will say I will use magenta color, okay. So, because we have already drawn this, we have already obtained this, so magenta color, and let us run this design. Oh sorry, here no need to change, because we already running it from here. So, here I am using, I want to use magenta color. Okay. So, let us wait, because we set here again 1/3 of the, so they are same, like 1/3 here, both cases the crossover frequency is set to 1/3. So, I have designed by means of pole placement and then it will give the value, where in output feedback we set 1/3 of RHP0 crossover frequency, here also we set 1/3 of the RHP0, and let us see what happened in the response of the converter. Okay. So, we will find if we, so this blue one is the response coming from the output feedback design, and that is using 1/3 of the RHP0, and you have the red one is the stress coming from model matching. So, I think so this is, that means if you go here, so the red one is coming from my small signal model of the output feedback design, and the blue one is coming from the output feedback switch simulation. For state feedback I am not using model matching, but you can try it out, it is not difficult because you already have the closed loop equation, but here my objective is to compare. So, if you compare these two results, you will see this goes to this value, this response is for 1/3 of the RHP0, this is kind of a overdamped response. I mean, it is overdamped, so you have the flexibility to increase the gain, okay, but this has overshoot. Now, I want to increase the bandwidth of the original design, that means I want to use, let us say 0.5, and here I do not want to use this because model matching I do not want to go, because I want to first compare the response, and the state feedback design I am using red color, whereas okay. So, let us go, and I am using half. So, it will show 1 minute. So, what is happening? So, it will show this, it is like I am trying to achieve half. This is a response, because I want to increase the bandwidth. So, this is my half value, I want to increase the bandwidth. Now, that means I am trying to achieve crossover frequency half of the RHP0. Now, I want to design the same thing using pole placement technique, that means state feedback approach, but it is current mode control. So, then if I use this, and let us see what is the response of the boost converter when you design the compensator by means of a closed loop, by placing the pole where the crossover frequency I have linked with the RHP0. So, it is RHP0 by 2, sorry, here I have to change it, I am sorry. So, I have still kept this. Now, this response is not correct. So, I have to stop the simulation because we have used 1/3. So, I have not changed it. So, now it is sluggish. Yeah. So, let us change it once again. I want to achieve 0.5 times of the RHP0, okay, and this case I want to use the design which now I am setting half of the RHP0, okay, RHP0 by 2, half of the RHP0. I want to compare whether using state feedback design approach can we really improve the performance or not, that is our objective, okay. So, now this is a response that I want to show. You can see the response due to the state feedback approach is much better because there is no overshoot. So, it reaches steady state almost same time, both of them are reaching steady state almost same time, but the first approach using output feedback has a high overshoot undershoot, and that is something not acceptable. So, I think our original discussion, that means using the state feedback design approach, we can leverage the more flexibility because we can increase the crossover frequency and we can improve the response without having overshoot. And of course, in this approach we are taking all these 3 poles into consideration. That means in earlier case there was a pole 0 cancellation, but now it is not there. So, the whole system is perfectly controllable. Now, we can use optimal criteria in order to not only for performance improvement, we can set some optimal criteria like LQR criteria for certain cost function optimization. That kind of criteria we can use. Okay. So, that means but only here we are considering a current loop gain, which you may not need to change in analog control. In fact, in analog control we will use offline design, because we do not do generally real time tuning. Then offline design, this state feedback approach, we can simply set a current loop gain, and this approach can improve the performance much faster as well as much better, because there is less overshoot compared to the traditional output feedback approach. Okay. So, that means this method is very useful for design of current mode control. Even for buck you can try it out, but for boost you can very perfectly manage, because of the RSP0 we have a constraint we found in output feedback. If you want to increase the bandwidth, then your phase margin was affected, but here there is almost no overshoot. So, it is nicely respond. So, but if you go to digital control, in real time tuning you can easily incorporate the current loop gain. Okay. And by that way this approach can be very useful for digital control, current mode control design. So, in summary, we have discussed design of boost converter under current mode control. We check model validity using MATLAB AC transient simulation. We have discussed limitation of output feedback based approach. We have identified what are the trade-off, and then we have discussed how to design state feedback current mode control using state feedback based design approach. So, with this I want to finish it here. Thank you very much.